Okay, so the first integration method that you saw or that you've learned before is called substitution. Here is what it is. Let's make this bigger. So it's used to transform an integral into something easier. Let's take a trivial example. Let's say 2x cubed dx from 0 to 1. Let's also parallelly think of it in terms of area, as we're trying to find the area of this shaded region here. Now we don't know how to find this area. Assume for the moment that we don't know exactly how to find this area. Idea is, can I transform it into a shape whose area is easy to find, like a rectangle or a triangle? So I say let u equals x squared, then du over dx is 2x, or du equals 2x dx. Now I can rewrite 2x cubed dx smartly as x squared times 2x times dx. Observe that u is x squared and du is 2x times dx. And because of how u varies with x, it is 0 when x is 0 and 1 when x is 1. So what happens is you get 0 to 1 u du, which in area terms corresponds to this right triangle, which is simply half times base times height, or 0.5 units. And now you can verify. If you take the original function, you can verify because you know the antiderivative of x to the n, and it comes out to 1/2. So what this illustrates is, using u substitution, what you're trying to do is you're trying to simplify your integral into something that is easy to find. Yeah. So there are sometimes I'm not going to go over examples, but if you practice questions, you'll get an idea of how to work with the substitution. It's kind of like solving a puzzle, so there is no one rule fits all kind of situation here. You kind of have to think about it a little bit. The focus of this week is going to be this method called integration by parts. Since integration is a reverse of differentiation, we're going to see similarities between the rules, right? There was a method of differentiation where we used product rule, and that is the inverse of that is just integration by parts. So here's the goal. Given function fx and gx, can I find the antiderivative of fx times gx? So we begin with the product rule. Product rule is derivative of fg is fg prime plus gf prime. You can visually see this as ff prime, g prime, and you get these small rectangles here. Or I can say that the antiderivative of the right hand side equals fx times gx by the definition of it being opposite operations. I can split the integrals and I keep the first one. So I say integral of fx times g prime x is fx dx minus integral of gx times f prime x. Now what you notice here is that the integral on the left side is f and g prime, and the integral on the right side is g and f prime. So they are slightly different. Now this is not really what we wanted, but it's still good enough in the sense that the right hand side is a product of, or the left hand side is a product of two functions. Okay. A neater way of writing this can be arrived by using a substitution. Let u be fx, then du is f prime x dx, and let v be gx, then dv is g prime x dx. So we get u dv equals uv minus v du. Example, x sine x dx. So let fx be x, f prime x is 1, g prime x be sine x, gives you gx is negative cosine x. Substituting it back, I get integral of x sine x is x times negative cosine x minus integral of negative cosine x, which is negative x cosine x, plus integral of cosine x, which is sine x plus c. You can verify that this in fact is the antiderivative by taking the derivative. So the idea here is fundamental to all problem solving, is transform the problem into something simpler. Now maybe f times g prime is not directly integrable, so we rewrite it in terms of g times f prime, and that may be easy to integrate. So it does look like we replaced one integral by another, but in some sense the second one, the one that we replace it by, is an easier integral. Now we're going to look at some example. Log x. There's no direct formula for log x. And it doesn't look like a product here, but recall, it's a very classic trick in math, is you can rewrite anything as 1 times itself. So log x becomes 1 times log x. Now let u be log x, so du is 1 over x. Let dv be 1, so v is x. And this becomes x ln x minus integral of dx, or x ln x minus x plus c. Similarly, at this point, you can pause the video and you can actually don't pause the video. This is an important example. E to the x sine x dx. I start with u as e to the x, so du is e to the x dx, and dv is sine x, and v is negative cosine x. But I end up with e to the x cosine x dx integral. Okay, so we can apply by parts again with u e to the x and dv cosine x, and then I'm back to where I started. But if I replace this term here, I notice that I have two similar terms with a negative sign here, so I can take them all to one side, which means I add the same term, and I get twice the integral I was looking for equals something that does not have an integral, and I can find a result. This is an example of an iterative process, meaning you start with an integral, you end up with a second integral. When you solve that, you find your original integral inside it, and then you can solve for it. So this is a useful example, which is an iterative integral. You have cases you may have to apply integration by parts multiple times to finally get the desired integral. Okay, I'm going to do this in the next video, where another example of iterative integrals.